Hey everybody, welcome back this week in Prototyping and Mechanical Engineering. My name is Will Fischer. I am your engineering guide here. Just to reintroduce myself, I know it's week 3, probably everyone here has heard me give this spiel before. I'm a mechanical engineer by training. I've spent about 10 years doing this. I work as a freelance mechanical engineer right now, but I've worked in a variety of different fields, different places. And particularly my specialty is within prototyping, building things really quickly. So today we're going to take a look at all of fabrication from that lens. It should be really exciting. And so let's just hop right in. As you guys know from the last couple of weeks, it's going to be a speedy pace. So hold on to your britches. We're going to start off, of course, with a movie break. I just want to show you a little bit here of some really cool stuff. I'm like, what is this thing? This is a machine that makes paper clips. And if you look closely there, it's a wire bending machine. So this is an example of a forming machine where it takes extruded metal and forms it into paper clips. And it can make hundreds of paper clips a minute, which is just totally cool. Anyway, I find that video just wonderful. So we're going to talk a little bit about fabrication and why it's important. So I think that's one of those things that, I mean, clearly if you are out with the goal of building stuff. Sorry, I'm looking at the chat. Oh, audio is a little too quiet. Video is laggy. I'm sorry. Is the audio any better now? Let me see if I can turn up stuff. Hopefully, is that better? Okay, sorry. Okay, audio is better now. Thank you. Sorry, thank you for that. Sorry, I missed that initially. Anyway, so we'll just jump right on in then. So this is about fabrication. If you have questions, just leave them in the chat. I'll answer all the questions at the end, but I will keep an eyeball on chat as it's kind of going to make sure I'm not missing anything too crazy. So we're going to talk about fabrication, building stuff, making things, getting what you want out of the material you want. So a lot of what we talked about last week with respect to materials, we're going to revisit this week as we talk about fabrication, because the reason that I set that up like that is because fabrication is kind of fundamentally a material specific thing. So we're going to jump right into that. I'm going to divide fabrication into 3 categories. You can see 3 big boxes on your screen right now. You're like, well, I can count. I did it. Good work. We're going to look into 3 different methods. One is additive fabrication. That's where you're adding material onto an existing material to get the part you want. 3D printing is a really good example of this. And there are a couple of others that we'll go over. Subtractive is the opposite of that. And that's where you start with a specific amount of material and you remove material from it until you get the part you want. This is kind of the whittling a stick into a thing, carving, that sort of stuff. We're going to look at that in a way cooler way, which is machining. And I'm going to actually spend probably the majority of our time living in subtractive machining land. Finally, forming is kind of the third part of that. That's where you start with a certain amount of material, and then you just have the same amount of material when you end. And that's molding and casting and bending and that sort of stuff. Even cutting, in some ways, if you're keeping both parts of the material, is kind of a method of forming. So we'll talk a little bit about that as well. I'm going to tack that on at the end. That's a really important part of fabrication, but it's one that I'm not going to concentrate on so much. So we're going to go back and look at this. This that you're seeing in front of you is a cocktail robot I built in eBriade. We built in 2014. This is the 2015 model that we competed in the San Francisco Cocktail Robotics Grand Challenge in. You can see a picture of it right here on your screen. That's it full. 31 bottles go on the inside of this thing, which is a pressure vessel. And what you can't see is there's stainless steel tubing going into the tops of each of those that has been bent. That's our example of our formed thing, because we took a thing and we bent it to be what we want it to be. This is the vacuum chuck. It holds the bottom. It has a vacuum pump attached to it. It holds the bottom of a cup. Suction on the bottom so it can move the cup around without the cup tilting over. So you can see that in action right here and the greater thing. And that was subtractively machined on a mill, a CNC mill. And that's how I got those cool shapes in there, the face. And then I used additive, which I consider welding to be an additive manufacturing fabrication process, to weld this aluminum frame. And so we'll talk a little bit about welding and welding design. Actually, I'm going to spend a fair bit of time on welding as well, because I think that's really important. So that's kind of our basis of fabrication. I want to talk a little bit about what fabrication looks like nowadays, because CNC, the computer numeric control system, is pretty much a game changer for modern fabrication. In the very old days, you know, hundreds of years ago, you had to carve everything with a sharpened knife, or maybe you were chipping things out of stone a long, long time ago. Forging and casting came along, I guess, millennia ago, but they weren't really refined for a long time. With the advent of electronic controls and electronic actuation, then we could create fabrication that uses that technology. So that while it was invented in the 1940s, it wasn't really practical until the 1970s. And basically any machine shop you go to right now, interesting, I'm sorry my audio's not great. I can shift over to a different microphone if we need to. Make sure that's plugged all the way in and everything. Universal in the 2000s. So basically any shop you go to nowadays pretty much uses CNC machining. There are a few exceptions to that, but mostly those are people who have some really cool method far in the past, like the paperclip bending machine. It's not CNC. When you choose your method of fabrication, this is super important. You're choosing on a variety of different things. In the same way that choosing your material was kind of what we focused on last week, choosing your fabrication method is what we're going to kind of focus on this week. And what I want to do is give you some practical ideas for some common and doable at home fabrication that's less common than 3D printing. And I'll explain that a little bit more in a second. I love 3D printing, but you can find that resource elsewhere. So when you choose your method, you're really thinking about the thing you want to build and what you need. So as we talked about in the schematics and drawings section, tolerance matters. That's how closely things fit up, and how things are really going to fit together. Surface finish may matter for your part a lot, particularly if you have something that needs to have a nice, fine finish on it. You don't want to spend your life sanding. That can make a world of difference. And it's the same thing if you get a really nice 3D print. It doesn't have a really noticeable layer lines, but if you get kind of a crummy one, you might get like oozy stuff that doesn't look very good. Another thing that's really important is speed. When you're building something, if I can mill something in 20 minutes that would take my 3D printer 15 hours to do, I'm going to opt for my mill probably. And the trade-off on that is ease of design. The nice thing about a 3D printer is that I can just drop my materials, my CAD file in, some other slicing software puts it all together, I press a button, and it goes, and it can print while I'm not there, which is really nice. Whereas a mill, I probably should be there unless I really trust my CNC, and I have to spend time tool pathing it. So if I'm going to spend 15 hours tool pathing this part, it doesn't matter if I can make it in 20 minutes. If I can just print it in 15 hours, I might as well do that. So you want to think about those things together. What's the combined speed of this thing between design and the speed of actual manufacturing? Is my audio okay? Sorry, I'm looking in the chat, seeing stuff come up there. Trying. Hopefully it's all right. Anyway, I'll just keep trying. So another thing that's important to think about, okay, cool. Glad somebody's gotten that through, right? Another thing that's important to think about is how much of your part is going to need to vary. How much are you iterating this design? Like, for example, if I need 40 or so of I could do that. We'll be back for the video there. Okay, maybe that'll help some. So I'll be using it again later, but maybe that'll help. Might be using a lot of bandwidth here, even though there's a fiber building. So another thing that I want to think about is how much am I going to need to purposefully vary something, where I would need to go back and redo it a bunch of times. In that case, something like 3D printing might be really nice. So that's an important thing to consider. And material viability is really important. If I need something that's going to be conductive, I can't use plastic. If I need something that's going to be good at high temperature, again, plastic's probably not going to be ideal. Whereas, if I need something that is going to be non-electrically conductive, maybe a 3D printed housing or shell might be really good. Yeah, and the final thing that's really important is what tools do you have available to you? You know, like the old expression, if all you've got is a hammer, everything looks like a nail. Well, that's really true in the fabrication sense as well. Part of the reason that I'm going to talk a lot about machining is because that's where my expertise is. When I learned to do prototyping, 3D printers just weren't all that good. They existed, but either they were very expensive with resin printers, or they just didn't have the accuracy we needed to do what we needed to do. And so the machine shop was our app was the only option we had. So when you think about things, these are just a couple of things you need to think about. And if you're going to be farming out your fabrication to somewhere else, then price is going to start to factor in as well. And machine shops almost certainly are going to be more expensive than a custom 3D print shop. That's just the sad statement, though it depends again on material. Let's talk a little bit about precision. So we talked about tolerances with respect to your design. And I just want to take a look at precision with respect to different fabrication methods, because different things, my microphone's on my jacket. The different things have different fabrication methods. So with flame cutting, that's almost a hand process where you take a torch and cut through something. Hand grinding is where you're at a grinding wheel actually grinding something. And you can actually get things by hand pretty well below millimeter tolerance, kind of by eye. And I want to point out that this line right here in the center, that's about a human hair's width. So when you're talking about CNC milling or CNC turning, you are getting orders of magnitude lower than that in the really, really fine machining areas, which is so impressive. And when you're talking about stuff like grinding, like CNC grinding or honing and lapping, the precision on that is so preposterously tiny. I mean, this is 2 microns. That's nothing. So that's a really impressive precision that you can get with some of these manufacturing protocols. I mean, you can't, at least right now, you can't get anywhere close to that on 3D printing. We will talk about a couple of these non-traditional methods as well. Actually, plasma cutting out is better than it has been here. I think you could get it into this area. Nowadays, it's gotten better since this chart came out. EDM we'll talk about, we'll go over those all later. Okay. Surface finish is another thing you need to think about. When you cut or grind, you have different surface finishes, and those are measured in what's called an average roughness, RA, roughness average. And you can get that in microns, or if the worst unit of all time, the micro inch, which is a real unit that I have used in real life and specified on real schematic drawings, which is a millionth of an inch. And that gives you an idea, and I have these up here so you can get an idea of kind of what that finish would be like, because that varies quite a bit. You know, kind of a rough surface as machined, you can get an as machined surface usually is about that kind of 1 micron, half a micron area. Whereas, you know, if you sanded that, you could get down to a 150 grit. Or a 320 grit will get you much lower. And if you really want a mirror finish, you could take out the polish paper and really go to town on that. Yeah, so that's kind of that. And you can get much finer surface finishing with some of these other techniques. So this is something where you might have a finishing technique that will come along afterwards to get you a nicer finish. So that's kind of our introduction to fabrication. I really wanted to spend, because I got some feedback last week that I was moving very quickly through things. I wanted to make sure that I spent time diving further into specific things so you get a little more value out of that. And so I didn't have to hurry myself up. So I wanted to move in on that. So jumping right into additive machining. So I would consider additive machining, additive manufacturing, additive fabrication, all of those are kind of the same thing. And that's, as I said before, adding stuff onto a thing to make your part. So I did want to cover 3D printing is really an amazing technology. My 2 favorite 3D printers are up there right now. Markforged and Form 3 from Formlabs are ones that I have here in my co-working space. I adore those 3D printers, and I use those parts all the time. They are just awesome. And there are a lot of great at-home 3D printers. I have a 3D printer that's a filament printer that I use. It's my personal one. I love 3D printing. Not here to slam it, but I do want to talk about welding and machining, and so we're going to not talk about 3D printing to get to that. And there are other additive types of machining that we won't talk about at all today. Most of those require high vacuum and like tons of infrastructure that are really a pain in the butt. So let's talk about welding. That's the one that I really want to talk about because I feel like there's a lot of designing of larger systems that require thinking about welding. So I want to talk about, this is the welder right here that we have here. This is a Stahlwerk 135M. I actually got it sitting right next to me over here. I wanted to have my torch here so I could show you just about how big this thing is, because this is going to be relevant when we talk about how you design parts for welding. So fundamentally, welding is about using, in this case, heat to join pieces of the same material with a filler material in between. So, so in this case, metal welding it doesn't necessarily require that. I've gone and put a star next to the ones where that's truly the case. And I want to talk a little bit about the other ones, and then we'll get really into the depth of those. So you can weld plastics. Plastics can be welded ultrasonically, which is super neat. They can be welded thermally by melting them together, and they can be welded chemically. There's solvents that you put in and they infiltrate. We're not going to talk about that. We're not going to talk about spot welding, which is where you use electrical resistance to create heat, and you can do it like immediately. That's super cool, but we're not talking about it. Nor laser or friction welding. Friction welding, which mostly happens accidentally when you don't put oil in your internal combustion engine and you weld your cylinders in place of the engine block. Don't do that. Makes your inner mechanical engineer sad. But I do want to talk about MIG and wire feed, TIG, tungsten inert gas, and oxyacetylene, just a tiny bit, and the design for those things. So those differ. MIG uses a wire feed to push out and then shields the gas. Tungsten inert gas uses a tungsten electrode with a shield gas and filler rod, and oxyacetylene uses a torch that's actually got flame coming out of it, and you're going to use filler material on that. So fundamentally, welding is about having a heat source. I'm going to not talk about the oxy torch a little bit here. I'm going to talk about this electrical arc as my heat source. And I'm going to use that heat source. I need to shield my molten metal from oxygen while the weld is cooling. It's really important because, as we talked about last week, oxygen in the environment will corrode metals. And it does so at a much, much, much accelerated rate if I've got my higher temperatures. So that's a temperature, it's a temperature dependent process. And so I want to shield it particularly while my metal is molten. And so what I do, I have two ways to do that. Either I can use flux, which is a material that floats to the surface of the weld pool, hardens, and then keeps the oxygen away from the weld while it's cooling. Or the much preferable way to do it is with shield gas. And shield gas is something that displaces the oxygen around the weld and fills it in typically with argon or CO2 or a blend of argon and CO2. And those are non-reactive or potentially even beneficial. The carbon and CO2, if I remember, will react with the steel to increase the strength of the weld. And you need to add filler material in because the heat of this electrical arc does vaporize some of your metal as it's molten. And so you need to add additional material in, or you'll burn through, melt away your material, and you'll be left with nothing, which is so sad. And so either you have this wire feed, which you can see in this thing here, and whenever you pull the trigger on your weld gun, it automatically feeds in. If you have shield gas, it'll automatically open the thing, and it'll automatically turn on the circuit, which makes it just so easy. It's like using a hot glue gun, but you don't even have to pump it a bunch of times. You just put it down there, and all of a sudden you're flowing liquid metal. It's awesome. I highly recommend doing this at home. Make sure you have the proper protective equipment, which we'll talk about a little bit later. If you are using a TIG machine or an oxy torch, you'll do that with a filler rod. So you'll actually have a long, thin piece of material. You'll have your shield gas somehow. You'll have those two things, and it's a two-handed process. So you've got your heat source typically in your dominant hand and your filler rod in your off hand. All of this stuff takes a lot of dexterity and a lot of practice to get right. I'm a welding instructor as well. I actually taught a welding class earlier today. And so I have a lot of practice on this sort of stuff. So it's quite easy now that I have a lot of practice, but in the design stuff, which we're going to focus on today, not necessarily how you fill stuff in, you got to think about this sort of stuff. And that's important because you need to think about the way things fit up. And so weld penetration is an important part of your structural capacity. If you have two pieces of 6 millimeter thick steel, but your weld only, and you're trying to join them together, but your weld only goes 2 millimeters in, your part will always fail at the weakest point. So you're going to fail along that weld because you didn't get your weld penetration deep enough. Most conventional wire feed welders are going to have a lot of trouble welding any thinner material than 2 millimeters. It's just going to burn and melt away. So when you design for a welder, if you're using big pieces of tube, so like I'm going to switch my video over here. If we could switch my spotlight to this one. I've got my welded component here. We're going to look at a whole bunch of different parts over the course of today. But you can see my welds are in here. So this is actually done by a professional welder who's ground the welds back down here to be flush. But you can see that my end material here underneath here is about 2 millimeters thick. And so I don't want to go much thinner than that because I'm going to have trouble welding that without burning through. Cool. That's welding. I'll stop the video there. Move that back out of the way. So that's an important thing. So that's okay. It's telling me to unmute myself, but no, you guys can. I hope. You can go a little bit thinner with TIG. In fact, if you're really, really delicate with TIG, you can go down sub-millimeter. It's tricky and it requires a lot of practice. You're going to burn through a lot of material first. One of the really important things in preparing your weld, if you're going to do it, is to make sure you have extremely close fit up between your parts. And that is, the closer fit up you have, if they're really flush, your weld will be much better. As you have a gap, what's going to happen is your material is going to tend to melt and run away from it. And that's a problem. As you design welds, your torch has to fit physically into the location where you're putting the welds. If you put two welds super close to each other in a really deep trench, you know, I've got my weld torch here. My welder, or me, if I'm my welder, usually I am, I can't get my torch in there to wiggle it around. So if I put components too close together, it's going to be impossible to weld. And any welder where you go and try and get a quote on a thing, they're going to look at this and they're going to give you what's called a no quote. A no quote is when a professional person who builds stuff looks at your part and says, hey, like, look, this is not a physically, I can't make this part to your specifications. If you get a no quote, just kind of as a general rule, what I would say is, I would go back to the manufacturer and say, like, look, what was it that caused you to no quote this? A lot of times they may even tell you up front, they'd be like, look, this trench is too deep, we just can't build that, or this tolerance is too tight or whatever. If you get a no quote, always go back to the manufacturer and say, like, okay, how do I fix it? And what else can I do? Like, if this is going to be super expensive, how do I make that better? There are different weld shapes, but all welds basically break down to functionally kind of one of three types. The butt joint down here that you can see, which is where I've got two pieces coming together in the middle next to each other. The lap joint where I have an overlap, so-called because it's a lap joint. And then this T-joint up here. And these other two are basically variants. This is basically a butt. The edge joint is basically a butt joint, and the corner joint is pretty similar to a lap joint. But that T-joint is the hardest to get a torch in. So when you design for that, think about getting torch access into your weld point. The easiest access is always going to be that butt joint because you can just come right up to the surface and get there. But when you're designing your weld, think about making sure that you can get all that stuff that fits in there. When you select materials for your weld, if you're going to do it with a simple wire feed like the one that I've showed you, you really can't do anything other than mild steel. Conveniently, mild steel is cheap, it's available, you should be able to get it anywhere. You can cut it out of other stuff, put it together, put it back together, super nice. And so you want to use a mild steel, and by mild, I mean low carbon content. So like a 1018, perfect for that. If you need fancier materials, then you need fancier types of welders. And this is where your TIG really comes in. For aluminum and stainless, you'll need to have that argon shield gas in place. And with aluminum, you have to have an alternating current welder because just the nature of the electrical process in aluminum, you have to use an AC welder. And so you need a TIG to do that. You can't do that with a MIG. Actually, that may not be true. There are some MIGs nowadays that do that, but they tend to be pretty expensive. It may honestly be easier just to get a TIG and do it that way. Besides, having a TIG is really fun if you want to do this stuff yourself. They're not even that expensive. You can get them for like 500, 600 bucks now. It's amazing. And they're pretty good quality. Stainless, you also typically use a TIG. You definitely need stainless filler and inert gas when you're doing it. One final note on welding. When you are putting things in place, design places for tack welds to happen. As you're welding this material, you're creating a ton of heat. And what that does is it expands your material. So if your material expands, you weld it, and then it contracts back as it cools back down, you're gonna get this warping effect. It's gonna cause your material to warp up, and you're gonna get these wrinkles and these curves, and it's gonna just destroy potentially really expensive material that you have. Excuse me. I've been talking a lot today, and some of it's been in the metal shop, so my voice is kind of shot. So if you were going to do a long weld like this lap joint, you would tack it in multiple locations, so that before you started welding, while the material is all still cold, you tack, which I usually say is about a 3-second weld in that location, to make sure you bond those pieces together. And then you do your whole weld. And what happens then is, as the material heats up, your tacks prevent things from shifting around. And when everything contracts back, it goes back to the shape that you were in. So that's really important. And as you're designing for welds, you also want to take into account that a welder who's doing this weld is going to have to tack things in place as they're welding. So just like understand that. If you're going to be doing the weld, you can always go back and grind off the bit later. And that's a pretty good way to get rid of that tack if you don't like it aesthetically. So I prepared a fit up demo, but then I don't have it. I'm sorry. I forgot to say. So we're going to cruise right through that. On the plus side, that means we're moving along with a reasonable amount of time. Hopefully this pace is a little bit better than this time. I certainly don't feel like I'm cramming a whole bunch of material. We'll get right on to subtractive manufacturing right now. So that's what we've got on welding and weld design. Of course, there's a lot more to it, but this is kind of an overview. What I recommend on a lot of these things, if you're building it for yourself, if you're prototyping, go and build it yourself. Try it. And see what happens. With welding, always run a test stripe on sample material before you do, to make sure your welder settings are dialed in. Subtractive manufacturing is where you start with a large piece of material. Maybe sometimes it's called a billet or an ingot, depending. Stock, round stock. There's a lot of different terms for this big material, and then you're going to remove that material until you have something that you want. So like this right here is a gear that's been EDM'd. That's electrode discharge machining, which is super cool. We'll talk about that towards the end of subtractive. And it creates this incredibly fine burr-free part. And you can do it on really hard materials, which is neat because you can't do that elsewhere. But I do want to spend a fair bit of time talking about milling specifically, because it's wonderful. We'll get to all of these other ones, but it's pretty awesome. So we're going to talk about cutting, which milling is. So this thing milling is super interesting, and you differentiate milling from lathing and sawing. All of them are cutting, which importantly requires the sectility of the materials. So as we were talking about material last time, metal and plastics both tend to be pretty sectile, in that you can shave them with a sharpened blade, as you can kind of see here. So this is actually an image I've taken from the mathematical underpinnings. These are two different theories of machining, and I want to get a close-up video of this as we're going. And we'll get to that in a sec. I just want one tiny thing here. Milling and drilling, you have a piece of stock that's relatively static, and you have a blade that is spinning around really quick in a circle that's removing material. Lathing, on the other hand, takes your stock, spins it around really fast, and you have a fixed cutting implement that cuts against it. And so that's an important distinction between milling and lathing. And that has really interesting ramifications in the design also. Sawing is much more reasonable. It's teeth that move all the way through a material to reduce the material that's in it. So we're going to have a quick movie break here to watch this, which I just think is the most hypnotizing thing ever. So this is that math. This is a cutting blade moving through steel. So that material on the right-hand side there is steel. Yeah, so you could just see it kind of cutting, and you can see the sectility of the material there. There's 5 minutes of this. We're not going to watch all 5 minutes because that's a waste of time. I see a question already there already. Isn't it turning rather than lathing? I use those terms interchangeably. I think those are kind of semantic differences. But yes, technically it is. The material that comes off of that, I think this is really funny, is called swarf. That's actually the real name for the material. So when you see those curly cues come off of your lathe, that's what it's called. It's a real thing, not making it up. So the general thinking when you're doing CNC stuff is that you have kind of a process flow that looks like this. And this is true for milling or lathing or turning or CNC grinding, any of these CNC processes. You start with a CAD model, then you go into what's called CAM, computer-aided manufacturing, computer-aided machining. And your CAM software will output a post-processed G-code. This is the same as your slicing software on a 3D printer, if you're familiar with that. It's basically compiling a set of three-dimensional tool paths into a coordinate system that is then parsed by your CNC machine. So you can see that over here. So this is a human-driven process of design. Tool pathing is also a human-driven process, and it can be quite labor-intensive. You've already designed your part, but you have to think about how everything is going to move through. I have honestly built parts where I spent 3 hours designing a part and 40 hours tool pathing it. And that, I mean, this is like seriously something that can happen. Afterwards, you end up with this G-code. As you can see, it really looks like coordinates, and these are moves. So M6 T1 is a tool change. M03 is a spindle spin up in clockwise direction, which is conventional. This is showing my Z height, my rapid transfers. And then I've got my moves at specific feed rates denoted by the F. Anyway, you don't have to know any of that sort of stuff because your post processor is handling all of that magic for you, which is super cool. When you're milling, there are some things that are very easy materials to mill, like aluminum. Some things that are hard to mill, like steel, and some things that are just like silly difficult to mill, like tool steel and stainless. Those are just let someone else do that. Farm that out to another shop. Even mild steel, it depends whether I would want that on my own CNC, because the harder a material is to cut, the more rigid a mill you need to cut it. And so those tend to be much more expensive because they require much more material to have that rigidity to make sure that it's moving properly, and much stronger actuators to push against this cutting implement as it goes. So you can mill aluminum and brass, plastics on much less rigid machines, and that's great. If that will work for your application, it's so much easier for you and for your machinist to do. I also want to show this part is milled, and you can actually see what's called witness lines on there, and that's the path the mill took. So those are microscopic features that create macroscopic visual things. So that surface is probably very smooth at the bottom. And in fact, I can show you some milled parts. Show you some milled parts over here. If we could shift our spotlight back over here. So I've got a clamp that I milled out of aluminum here. And you can actually see those witness lines inside there. So I bolted this down to my mill table, and then I used my mill to cut out that. So I actually want to keep looking at that for a second, because I want to talk a bit about tool access and how I've got tool access. So a conventional milling bit looks like this. So this is just a standard, this is what's called a square end mill. And it's called that because if we look really closely here, I hope you guys can see that, the end of it is square. And I've got a slide that shows this up close so you can actually see. Actually, you can see it on the slide right now. So that's a 4-flute square end mill on the slide. And I've got a 2-flute right here. And I choose my flutes. This is kind of getting into deeper machining for the purposes of chip clearance. So more flutes will get me a finer surface finish, but it'll struggle with materials that need to have the chips cleared out really fast, like wood or aluminum or plastic. So I'll get a plenty fine surface finish with a 2-flute on most of my softer materials. Yeah, so then when I'm looking at it, what I can do is I use multiple tools to get the things that I need out of this. So I'm going to do roughing with a relatively large bit like this one. So I'm going to rough around in here, and my CNC will control where my material is getting removed. And then for finer stuff, holes or the trenches that I used, because I actually made this originally out of a single material, I used a much finer end mill. And you can get really tiny ones down here, down to, this is less, this one at this end is less than 1 millimeter in diameter. And so I can get really fine features in there. And this I actually did, so I'm showing you this all from the top, but I actually did this on a 5-axis mill. And so I actually milled parts of the sides here as well to get my holes to line up properly for my little clamp. Yeah, so then I've put some screws and stuff in there so that I got my own little clamp. And that's actually made so that I can clamp another piece of materials. This is round stock. This is a brass, easy machining brass that I wanted to cut something out of. This was a failed attempt at cutting the part that I needed, but I needed a way to clamp it in properly to my machine. So this is the clamp that I built for it. Here. And now I can't get my clamp open. There we go. So one of the things that's really important, if I look at this, you'll notice at this part, so I'm going to show it as close as I can get in there, that I have relatively sharp corners on the edge here, where my finger is right there, but I have perfectly rounded shapes on the inside. And this is really necessary. And the reason for that is I need my spinning tool to have access in there, and I can't make an internally sharp corner with a round tool, right? This is the square peg round hole phenomenon. But on the outside, I can't, because what I can do is I can just trace around a straight corner, and what'll happen is I'll get a 90-degree angle. So that means my external shapes are arbitrary, but my internal shapes must have at least some curvature. And in the next slide, I'll talk a little bit about that. So I'll set that down. And I just want to say that you can machine very, very fine parts. So this is a gear that I needed, a 9-tooth bevel gear, and I 3D printed one out of resin here. So that's 3D printed on that Formlabs tool. And then I machined the same part here. Now I've got it in a collet, so you can't see it because I needed to go and do some more work on it. But you can see actually from a precision standpoint, my precision is actually extremely good. In fact, I probably got comparable precision off of that 5-axis machine, better than I would ever have gotten on a filament printer, and getting close to what I would get on a resin printer. So pretty impressive stuff off of that little machine, which I really like. So I'll stop my video there. One of the things you also want to think about before I move on from this slide, so if we could take my spotlight back to my screen share, that'd be great. So people don't have to look at the picture of me without hair. Spotlight back to the talking me. There we go. Okay, thanks. So you see my screen share there. Here's the 4-flute end mill, this is doing this. So the machine that I'm talking about, the 5-axis, is what's called a pocket NC, which I really like. We have one here that I think is just an awesome, awesome machine. One thing that's important when you're clamping, you need to clamp hard enough that your material doesn't move during machining. Particularly if you cut too aggressively, your bit will have a tendency to catch, which can fling your workpiece off to the side. That can be quite dangerous. So having an enclosed mill is a nice thing there if you have it. If you don't, that's not ideal, but happens. You also need to be able to clamp without deforming your material. So this is not so much a problem if you're doing metals, but if you're doing plastics, particularly ones like Teflon deforms a lot, and then you machine, and when you unclamp, all of your holes go from being circular to being elliptical. And so it's really a big pain in the butt. If you're machining Teflon, you have a very specific thing in mind. I would not machine Teflon unless I had a chemical application in mind. So if I was building chemical vats or something like that, then I would do that. Otherwise, use Delta, which doesn't have that problem. Here is a snapped end mill. If you are a machinist, you have snapped an end mill. This is just the way that it is. If you cut into material too quickly, if you don't have enough oil in your part, whatever it is, you're going to snap some end mills. But very important in your machining design is that you keep track of several of these major factors in your design. So feeds and speeds, these you look up in a table for your material. And your material will tell you usually surface meters per minute, surface feet per minute, and inch per tooth. So cut load, chip load down here. Yeah, those will do, it'll tell you that. And it'll tell you a good depth of cut as well. A lot of times you'll have what's called a machinist calculator that tells you all of this stuff as you're designing. Important for your design, however, is that you maintain a tool aspect ratio of 4:1, and I've got some images in the next thing that'll show. And that you have your internal thing so that your depth, your vertical height to the interior curvature is that 1 to 3 to radius. And these slides will be up on the project page so you can take a look later. A movie break, I just want to show you what a 5-axis machine can do. This is not the one I use, but it's just cool. So this gives you an idea of that tool access. So here you've got a 5-axis machine that's moving around. So you can see that it's getting those really cool chamfered edges off of a square end mill, which is just super neat. Anyway, it does this for another 5 minutes. We don't need to watch it. Back to what we were working on. So when I was talking about cutter shapes earlier, I was talking about the square end mill, which you can see here gives that nice square bottom. You do want to think about your milling design from the side. And I think that's really important because that indicates you're going to think from 2 angles. You're going to think from the side. So if I've got my square end mill, that it's going to come in along here, like I'm seeing here, and then from the top, where the axis of rotation of my mill is going to be, because that determines where I'm forced to have those curvatures from the tool rotation. So from the side, you've got a whole bunch of different options. The square end, the ball end, the rounded edge, which is also sometimes called a bull nose, which is confusing when you have a bull end mill and a ball end mill. Be careful, I've made that mistake before. It's a real pain. These are some less common ones that you see around. Chamfer is pretty common, but slitting and key seat are relatively uncommon. Dovetails and T-slots, those are pretty convenient if you need to have undercut features. And I'll talk about that a little bit more in a second. Corner rounding are fairly common. The ones over here are really pretty uncommon. So let's talk about some of your design stuff here. This is a great way to design for milling. You'll notice that my features don't have any overhangs. I have my aspect ratio is good in such a way that I can get good amounts of tooling in there. And my minimum feature size down here is pretty big, and I've still got at least that 4:1 aspect ratio, meaning that this feature thickness between here is not less than 4 times the height of this feature, right? Because that determines the size of bit that I can fit in there. If I get more than that, then I'm gonna have a tendency to snap bits. And I can have through holes in milled parts. That's allowed. I can do that, which is really nice. This part is a trickier part to manufacture. Still doable. My aspect ratios are still all okay, but you'll notice that I've got this undercut here. And I could do that with a key seat router or key seat cutter. But that's a big pain and it's hard to line that up, and I'm gonna have trouble getting everything in here to match up and have a smooth bottom on that thing. Even with a CNC, I'm gonna have a tiny gap where I had zeroing issues on that. This part is literally impossible to make on a mill because I have a very deep undercut here and I don't have the tool access to get it from the bottom side, and my bottom side, so at the very best, I would have to machine in from this side and this side. I'd have to clamp it twice, trying to make my features match up. That is a huge pain in the butt. And even so, I don't have any way to get any tooling into this space. So I don't have any access from this side either. So we'll talk about it here as well. Another set of things. Here I'm doing, like I said before, my 2-sided machining features. If I'm putting features on 2 different sides, curved surface, something like that, that makes it just harder for me to clamp it. Because now I have to orient one side, machine, and flip it over and orient another side. So I'm going to lose track of my orientation between those 2 sides. And if I want features to match up, then it's going to be really, really difficult. And I'd rather not. I'd rather be able to mill it in one single clamping session, all from one get-go, like my Hooray over here. This is possible, this part over here, but I'd think about how many places I would have to machine this part from. So I'm going to have to drill a hole in here. I'm going to mill this here. I've got an undercut here where I need to use a key seat. And then I have to clamp over on this side to do over here. And I have to clamp again over on this side to get that feature in there as well, right? That is a big pain in the butt to make that part. So if you can, avoid designing like that, if possible. All right, that's what we've got for milling. And I do want to move along. I notice I'm 45 minutes into my hour class and I got a lot more to cover. But I wanted to get deep into design for milled parts because I think that's something that's really important. Lathing has very similar constraints to milling in terms of tool access, in terms of constant things, but it's really nice for some things that milling doesn't do very well. It's excellent for highly concentric parts. If you need a shaft that's going to rotate at high RPMs, don't mill that, please. Put that on a lathe. The lathe is already turning that. And so you're guaranteed to get that really nice concentricity, assuming that your lathe is dialed in properly. If you have a nice enough lathe, it'll be like that, assuming your run out isn't too bad. In the case of lathing, you want to design your part from the center plane. So section through your part on the axis of rotation, and then design that way, because that's where you're going to have tool access. You can do interior cuts with lathes, and you can use what's called a grooving tool to even get those undercuts in there. And I want to show you kind of what a lathe looks like in case you haven't seen one. Just a really fast video here of how a lathe is doing this. So you see that my part here is spinning around, and I've just got a cutting tool that's static relative to the rotation of the motion there. And so that thing in there is going like that. And so I can cut that and get that nice smooth finish. Lathing can get much finer surface finish than milling can, because you can move that cutting tool over a very, very, very gradual bit. So you get extremely nice surface finish on your lathe. When you're doing lathe work, you can do really cool concentric stuff by using your tailstock. You can put, most tailstocks will have a drill bit thing, so you can put a thing in there so you can drill in, you can chamfer those corners, you can get really nice parts out of that. You've got this cross slide which moves in and out to set your tool depth. This is a manual lathe. Honestly, if I'm putting together a shop from the ground up, I get a CNC mill and a manual lathe, because there are very few parts where you can't do it manually on a lathe, where you would want a CNC, unless you're doing really cool like curved surfaces and stuff. I don't know, for functional stuff, for engineering parts, it's rare that I would want a CNC lathe unless I'm doing high throughput, in which case I would probably farm that out to a shop. Okay, we had our optional movie break. That was the one I just showed. With lathing, your chucking is really important. You're going to chuck a piece of cylindrical material into this 3-jaw chuck. You can also do hexagonal material. With your 4-jaw chuck, you can chuck all sorts of crazy stuff, which is great fun. But you're going to end up with circular shapes out the back anyway, because you're spinning it around really fast. That's just the nature of it. But if you want to start with square stock, you can make your square peg into a round peg for your round hole in your square. I've just confused myself. Here's a higher order CNC. So before I saw in chat, the 5-axis that I was using is actually this little pocket NC. It's great. It cuts brass and aluminum. It's not perfect, but it's really cool. It's built off of, I think it's built off of Beagle Bone on the inside, and it has a web browser that you just upload via USB to, so it hosts a fake web server. Super neat, super easy to use. It comes with a little clamp that is just terrible, and I recommend bolting your parts all the way into it for that, but you can get some really nice parts out of it. So this gear that I was showing you earlier is from that tool. They are a big pain to program. 5-axis programming, like I use Fusion 360 both for my CAD and for my CAM. It's nice because it's integrated and it takes into account part changes in my CAM. Man, that little gear took me probably 40 hours of programming to get it to cut at where I wanted it to. But I was able to cut the same part out of brass, which is amazing because you can actually get like really functional parts out of it. You know, I needed to lift a bed, and so I was shedding teeth off of my 3D printed gears, but then the brass part would have worked if the company hadn't dissolved. I'm not bitter. So many of the same design constraints apply that you would have in your 3-axis manufacturing, your 3-axis milling, to your 5-axis. But the nice thing is you have tool access from multiple different sides, which is really cool. Sawing is a whole field in itself. There are just a jillion different types of saws. Circular saws are really common out there. Table saws are really common. Jigsaws are really nice. Those are all wonderful to have. If I'm going to put together a shop from the ground up, first one I'm going to buy is a vertical bandsaw, like shown here. That's nice for cutting down pieces, but I can also do some delicate work. General theory on a bandsaw is you should have 6 to 8 teeth engaged in your material thickness. So if you have very thin material, use fine teeth. If you have very thick material, use thick teeth, like wide teeth spacing. Horizontal bandsaw is nice because you can put your material in, you can set it going, and you can walk away, and you get a very nice clean cut. They tend to be pretty expensive. It wouldn't be my first choice to have in my own shop, though I would always love to have one. A miter saw is really nice. You can cut it with aluminum. If you have a really strong one, you can use a grinding attachment for steel, which is awesome. But it's also nice because it guarantees you getting these really nice, clean 90-degree angles. If you're going to be doing a lot of welding, I definitely would recommend a miter saw over a bandsaw or a horizontal bandsaw. If you're going to be doing a lot of machining, I might think about the horizontal. And if you're just doing general purpose stuff, that vertical bandsaw is really nice to have. Grinding is really important also. It's necessary for fit up and for finishing your welds. An angle grinder is, I think, an awesome tool to have. I have one, I love it. If you get the chance, go cordless. They're just easier to deal with without the cord. But if you're looking for a bargain, you can get a corded angle grinder for 30, 40 bucks. It's a great deal, fantastic deal. A bench grinder is another really nice one to have, particularly if you're doing machining. It's nice to be able to go back afterwards and machine and to take off machined burrs with that bench grinder. This one that I've showed also has a belt sander on it, which is a nice bonus. So what I would do is I would get something like this that's half grinder, half sander, and then you get both covered. It's the same thing, taking up a small footprint in your shop. CNC grinding is a thing. You are never going to do that at home, but if you need an extremely fine, the finest, the best tolerance of any conventional machining you can get is CNC grinding. I mean, it's unreal the quality of stuff, and they can do basically any material. So if you need machined ceramics, you can get them custom ground, and that is ludicrously expensive, but very cool. Yeah, they can get that precision down to like, you know, single micron level, which is incredible. Polishing is also a type of grinding, and you can get optical clarity out of it. You can get optical clarity out of CNC grinding as well. They CNC grind optics for telescopes, which is awesome. I want to talk briefly about other subtractive manufacturing methods. Electrode discharge machining, which I alluded to earlier, is this one right here. You can see there's a big pool of water in there, which actually they use deionized water, which has all the ions taken out of it, so it's not conductive, which is super cool. And then it's what's called spark machining. And so what they do is they run a bunch of current through, and the spark ablates material off. And the cool thing about EDM is that it leaves absolutely no burr, even on extremely hard materials. So you can EDM stuff like tool steel and stainless steel and not leave a burr. So a lot of times this is used in gears and stuff that go into cars, because you can cut out these beautiful, perfect shapes. And it tends to be used for cutouts, though it can do three-dimensional stuff as well with CNC. Plasma cutting is another really cool one. There you're rapidly oxidizing through a piece of metal. So you need a conductive material, and it cuts extremely fast. You can get arbitrary two-dimensional shapes beautifully, but it's a through cut. Same thing with laser cutting. It's also a through cut. You can laser cut a variety of materials, but for metals, you're probably going to be shopping that out because you need a big, powerful laser to cut through metals. But you get really nice cuts, and if they've dialed in their process right, there's no burr on that either. You will get a bit of a burr slag, actually, technically, off of a plasma cut. Water jet cutting is another really brilliant one. Water jet cutting will literally cut any material. It's so cool. They actually put little pieces of what they call garnet into it. It's not actually garnet. It's just like a grinding abrasive material. And then they fire out through a nozzle at an extremely high pressure. And it'll cut through granite. It'll cut through steel. It'll cut through anything. Again, you only get a 2D shape, and your thickness is relatively limited. But the cuts that come off water jet cuts are magnificent. They're just perfect. So if you have money to throw at your project and you want just gorgeously made parts, I would look into one of those manufacturing methods, and I would farm that out to a local shop. And if I were going to do that, I might, even before I started designing, if you know you want to use a specific fabrication method, go and talk to the machinist that's going to be doing this for you and say, look, like, what are the design constraints? What's going to make your life easier? What can I do? How thick a material can you use? So on and so forth. Cool. So that's subtractive. I want to touch on forming as well, and then I'm going to talk us through 12 tools to own. So we do have to pick up the pace again, but I'm glad I got to slow down a little bit on that sort of stuff. Forming is something that can be done at home in some cases, and should not be done at home in other cases. So shearing is an easy one. Like if you're cutting metal, technically you're reforming it from one piece into two pieces. Punching, similarly, you can press stuff. You could even hammer stuff into a mold, kind of old-fashioned way. That's how they make, I think that's how they still make cymbals for drummers. Bending is something you can also do at home. I'll show you a little bit about that. Casting and molding, I'll talk about each of those. Probably not for at home is forging and diffusion bonding, and I'll talk about those also. So shearing, punching, and bending, you can all do at home. Shearing, you can do either with these nice automated shears. If you're doing sheet metal, that'll do up to a millimeter, maybe 2 millimeters of steel. You could just, and it cuts a centerpiece out, so that's got this little tool thing that kind of like wibbles around, and it It removes material from the center, which keeps you from deforming the edge of the material you're doing, which is nice if you're going to go back and weld sheet metal. You can also use hand shears. Those do deform the edges, and so you get this kind of crazy bend, but it's a whole heck of a lot cheaper, and it's a lot easier to just bust that out instead of having to plug something in. If you're going to bend metal, which I highly recommend, it's a great fun thing to know, you can actually create these little posts for yourself. What I would do is, if I have my welder, I'm going to weld 2 posts to a steel plate. And if I need a specific radius, I'm going to weld a tube of that radius on, and then another tube of that radius, and then I can just bloop, make sure I have that perfect thing every time. You can get a lot of punching stuff at home nowadays if you're doing light material, leather, or even aluminum. You can get steel punching stuff if you have a big arbor press to press it through. And an arbor press is just a big piece of thing with a gearing reduction that allows you to crank it. Injection molding is a form of forming. You're molding stuff. It's not something you can realistically do at home because it requires extremely high pressures going into a mold. I'm not going to talk too much about injection mold design because it's not my specialty. And I don't know a whole lot about it, but I just wanted to show you kind of what that system looks like here. You can do hand molding. So actually, I'm doing that a fair bit these days, where I will 3D print a mold, then take moldable silicone rubber, coat it, then cut it open, and then I can mold other stuff inside. Or I can 3D print something that I want to be made out of silicone later and do basically any thermoset inside of that, which is cool. And you can get some really cool stuff like that. And you can even do low temperature thermoplastics, including there's some very low melting point metals that you can melt inside of silicone. Woods metal is one of them, which is a gallium alloy. Definitely don't drink it. Handle it with caution because it'll seep through your skin. But you can get it and get metal parts cast in silicone molds, which is super cool. I do want to talk a little bit about casting. Sand casting is something that's also available for you at home. Lead you can melt with a conventional blowtorch. So if you want to make lead stuff, I have done this with radiation shielding that I had to make for my job at once. I've had a cool life. You can also do it with, you can also sand cast aluminum. If you have a hot enough kiln or forge at home that'll let you melt aluminum, which you can do with a carbon arc forge. There's some YouTube videos out there that'll teach you that stuff. It's kind of insane and really awesome. The way sand casting works is you build basically a sandcastle around your stuff. You create a part that you want to replicate, and you pack in the sand, and then you take it open, you open it, then you pull your part out, and you pour molten whatever it is in there, and then you get your part back out, which you can kind of see in there. You can also do plaster casting. There's definitely 3D printer burnout filaments and resins you can get, so you can 3D print a thing, plaster cast over it, burn it out in an oven, and then cast stuff in there. Forming, that's the stuff you shouldn't do at home. Forging typically requires a forge. This is a drop forge, so it's taking a piece of a hot billet and cranking it into something like a bolt. Diffusion bonding is a really cool thing where you put something in vacuum at very high temperature and apply a lot of pressure at the same time, and it gradually, the grains seep into each other and it comes out as a single formed piece. Just a neat method. Not much about that other than that. Okay, cool. I've got 2 minutes to go through my list of 12 tools to own. So I do want to hop in on that. We're gonna go back. Well, I'm not gonna show you. I've got all of these I have set on my desk so I can show you in frames. You can see a little tiny video of me. You're gonna see me pick up each of these things very excitedly because I love them. That's me looking really excited. Tools to own. I am trolling myself. Why did I do this to me? Okay, my number one favoriteest tool of all time is the standard single edge razor blade. I just love this tool. You can get good leverage with it. They come in 100 packs for $8. They're sharp as heck. And you can do all sorts of stuff with them. Other people like scalpels, X-Acto knives, that sort of stuff. But a blade is, simply put, the most convenient thing you could ever have. I even have one on my number 2. So I've got my good lighting here. And if you look, you can see I've got my magnets here. I leave my razor blade stuck to my light fixture. And so you can see I've got my good lighting, and I've got it so I can swing it around and get it over whatever I'm working on when I'm working. So that's number 2, is good lighting. Number 3 is a pair of calipers. And calipers are really necessary when you're designing because you just have to be able to look at stuff and think to yourself, gosh, how big is this thing going to be? So I have a pair of digital calipers like this. Really, any brand will do. You go on Amazon and they're maybe 15, 20 bucks. Definitely get a digital pair. The analog pair are cool. You get to feel awesome, but digital is just more useful because you can do stuff in multiple dimensions. Even if you're working all in millimeters, which you should be, you may want to have the ability to look in inches, because sometimes you're going to be buying tooling from America where things are in inches, and it's nice to know, oh, this thing's actually 1/4 of an inch instead of 6.35 millimeters. A driver set is really important. I've shown the one up there, the Vastar ones. I've got that one right here. I love it. This one has a bajillion pieces, and every possible thing you ever need to open, you can open with one of those. I also recommend a really nice Allen key set. I've got the metric one here. If you're in America, you want both metric and English. Tweezers are also really important. I have my fine tipped ones. You definitely need a pair of really, really, really fine tipped tweezers. And I also have a curved set as well. So if I drop a nut into something, I can fish it back out again. Yeah. Number 7 is kind of maybe unconventional. You can get what's called key files, but I honestly find a pair of good nail files. These are a nice made in Germany one. They tend to be good enough. You can file basically anything with these, and it's nice because you can get in if you're working on small parts to use these. Also, pliers are a must-have. I like these. These are my compound pliers. These are really nice because they you can see they kind of have that compounding action. So I can get really, really, really incredible grip on stuff. And that's for everything that's too big for my tweezers, but still needs to be grabbed. Sometimes I'll have a pair of needle nose pliers as well. I don't actually in my shop here, which I've wanted and have not had, but I would recommend those as well. PPE is really important, but it doesn't make it until number 9 on my list. Every bit of PPE you should have. Safety goggles, always have your own. If you're borrowing from the shop, they're gross. They get the big clunky kinds you can't see through. I like the kind that are kind of like fit like sunglasses. They fit closer to your eye, so they protect around the edges and they keep stuff from flying in around the edges, and they're just much more comfortable. So I highly recommend this kind. You always want hearing protection. I like over ear because it's easy to get on and off quickly. You can get the in-ear ones. Check the rating if you're going to be someplace really, really loud. And then work gloves. I actually really like these ones. These ones have a rubberized grip on them that lets me pick up stuff. And that's if I'm in the machine shop. I like using those. If I'm welding, of course, I'm going to use big, thick leather gloves while I'm welding, and a welding helmet because you don't want to go blind. Or even if you've got goggles, you don't want to get the sunburn off of your welding arc, which is a real thing. I'm a big fan of the Dremel. I like a cordless one. They go up to, 30,000 RPM, and they'll cut through, grind through, deal with anything. They are an awesome tool, and you should familiarize yourself with one. That's one where just a rotary tool of any sort, they're all really good. I went with the Dremel brand, but you can go with whatever you want. Dremel is a brand name like Xerox or whatever. You can go with any. I don't specifically endorse them. You also want to have a drill or an impact driver. This is a cordless drill. I prefer that. Makita is my favorite brand, but honestly, I've been using a lot of Bosch since I'm in Germany, and they're great. An impact driver and a drill are pretty similar. The difference between the two is that a drill has a chuck here that will let you clamp any size, let you chuck any size thing, and it contracts. Whereas your impact driver just has this little hex fitting, and it's much faster to pick up in and out, but you can't do arbitrary size drills. Plus, an impact driver, when it stalls, will push forward and then resume, and that lets you unstick things and crank things in way tighter than a drill can get. But it's also not great for actually drilling. Finally, one that I really like, I've got a picture of down here, I'm not going to pick mine up, is a soldering station with a heat gun. Heat guns are basically the best tool ever. That's not true. They're the 12th best tool ever. But a soldering station is nice if you're doing any electronics. Highly recommend having something that gets you both of these things. This one's similar to mine, but not exactly the same. But it's nice to have that there. So that's the 12. That's our whole agenda. I went a few minutes over. I'm dreadfully sorry. But I just want to remind you guys, engineering is all about iteration, prototyping in particular. Try stuff. Get out there into the shop. Get out there welding. I recommend finding your local hackerspace and getting some of these tools and access to some of these tools. A lot of these tools are really cheap. You know, a razor blade costs $8 for 100. You can use them a lot. Yeah. So that's it. Now you know how to build everything, including this delightful thing, which is definitely possible to build.